let's take a look at an interesting question. What if it's the case that I have a function with a first derivative of 0, and that is true for every single value I plug into that derivative on a closed interval, right? So my derivative it comes out 0. My function has tangent lines of slope 0 for an entire interval of values. Can I say anything about my function? Well, if you think about times when I've consistently had slopes of 0, we might start to guess that, like, well, maybe it's the case that our function is like a flat function, right? Like it's constant, because then no matter what value I choose in the interval, I always get a tangent line that's horizontal. So we might be able to say that, maybe our function is constant. That is, I have like my function actually just equaling a single value, like I have y equals 6 as my function. But how would I actually know if this is going to be true? So let's take a look at this. I can state that to prove this, let's suppose that m and k are unequal numbers in the interval from a to b. Okay, so let's just imagine for the sake of argument that I have these. So let's say that maybe the value of m is maybe sitting right here, and the value of k is sitting right here. So they're unequal, they're not the same, so one's got to be bigger than the other. Well, now I'm going to go ahead and think about what the mean value theorem could tell me. So I could say, by the mean value theorem, there is a value c between this value of m and k such that f prime of c is going to be equal to f of m minus f of k over m minus k. Now, you might be thinking, wait a minute, Kyle, how are you just using the mean value theorem? Don't you have to actually guarantee that your function here is actually going to meet the conditions of the mean value theorem? And I actually think that we have, because if my function is equal to 0 for all values on this interval, then certainly my function is differentiable there. And remember, if a function is ever differentiable on an interval, it is also continuous on the given interval. But here's what's interesting. If I know that f prime is always going to be equal to 0, right, no matter what value I have, then if c is a value in between, I know that f prime of c is a value, c is a value that falls between a and b, and so the derivative there should still be 0. And so I get 0 is equal to this fraction. Of course, then I can actually go ahead and I can multiply over the value of m minus k, and I'll end up with 0 is equal to f of m minus f of k. But then, of course, that must mean that f of m must equal f of k, right? They have to actually be the same value. But notice, since m and k were just any numbers inside of this interval, they were any numbers at all, then I can state that since m and k were just any numbers in the interval from a to b, this must mean that f of x is constant. This is really interesting, right? Notice, because I didn't tell you what values I was going to choose. I just said, let's pick any two values in the interval. They could have been any of them. And we were able to find that those two values always spat out the same y value from our function. So no matter apparently what I plug in, no matter what two values I ever plug in here, I always end up with the same output. And that must mean that my function is constant. We can kind of summarize this in the theorem that we have down below, which states for us something that's really, really important. If f prime of x is equal to 0 for all x in an interval, then my function is constant on that interval. That's really, really interesting. Now, what that ultimately means is that it's actually not ever then going to be possible to get a derivative of 0 with any other sort of function. And that may have seemed obvious maybe at the start, like, Kyle, the only way we've ever gotten derivative 0 is to take the derivative of a constant. But just because that's all that we've seen happen doesn't mean that we just, it doesn't mean that there wasn't another function out there that could have had a derivative 0. We just don't know. But now we can see that after we've developed this argument, the only way for us to have a derivative 0 is if our function happens to be constant.